I'm Lucas CIEZA from Universidad Diego Portales in Santiago, Chile, and I will tell you about the first image of the water snowline in a protoplanetary disk and why this is actually important for planet formation and astrobiology. So in the solar system we have 8 planets, but only 3 of them are located in what we call the habitable zone, which is the region around the star in which the temperature at the surface of the planet can be right to have water in liquid water. In the solar system, this region extends from about 0.7 astronomical units to 2 astronomical units. The Earth is in the middle of this zone, but Mars and Venus are also included in this zone. Of course, we know that the Earth is the only planet with oceans, and that's because Venus and Mars don't have the right atmospheres to have the right temperature at the surface. In particular, Venus has a very dense atmosphere, and therefore is very hot, and Mars has a very tenuous atmosphere, and therefore is too cool. But being at the right place is not enough to have water. In particular, all the rocky planets in the solar system form very dry because when the solar system was forming, the inner 3AU was very hot, and all of the water was in the form of vapor. And water vapor is very difficult to incorporate into rocky planets. So the water has to come from outside. We are used to thinking that there is a lot of water on Earth because 70% of the surface is covered by oceans, but in reality, the mass of the oceans represent only 0.02% of the mass of the planet. And this is because, again, the rocky planets form from dry planetesimals. The region that divides the dry planetesimals in the disk from the wet icy planetesimals is known as the water snowline, and it's actually very important for the formation of planets because water ice is sticky and allows for a much rapid growth of planetesimals and allows the formation of giant planets. The location of this water snowline is also important for astrobiology because it regulates the delivery of water into the planets that will eventually populate the habitable zone when the star is in the main sequence. And most of the water on the oceans of Earth come from wet planetesimals from outside of the snowline in the form of comets, of asteroids. So planet formation models usually assume that the water snowline migrates inwards. This is the location of the water snowline has a function of time for stars of different masses. And in these models, you have the stellar radiation, the stellar luminosity on top of plus the accretion luminosity. And for solar mass stars, you see that the accretion luminosity, this is the luminosity of the material that falls from the disk onto the star that creates an accretion shock, dominates over the photospheric luminosity. This means that the location of the water snowline will be set by the accretion rate of the disk onto the star. And in this particular model, for a solar mass star, the water snowline starts at about 5 astronomical units and moves inwards to about 2 astronomical units by an age of 3 million years. However, from star formation studies, we know that the accretion rate, and therefore the luminosity from accretion in protostars, is extremely variable at very early ages. And it goes down overall, right, as a function of time, but there are some spikes in accretion luminosity. These spikes can increase the luminosity by up to 3 orders of magnitude. And these are known as a outbursts. And these a outbursts are expected to happen several times during the formation of a solar mass star. These FURI outbursts typically happen at very early stages in the class 1 stage when the protostar is still embedded in a dense envelope, and at this stage the mass of the disk is of the order of 10 to 50% of the mass of the star. Eventually the envelope dissipates and the protostar evolves into a classical Tittori star. At this stage the mass of the disk is much less, of the order of 1%. This embedded stage is very short, lasts less than 1 million years. And the classical Tittori star stage can last up to 10 million years, but typically lasts 3 million years. Before ALMA, we thought that most of the planet formation activity happened in the classical Tittori star stage at ages of a few million years. But this really changed recently with the observations from ALMA that show these are the famous observations of HL tau. ALMA chose this class 1 protostar as one of the first targets for the long baseline observations and produced the high resolution images, in which we see that by an age of less than 1 million years, we already see indications of advanced stages of planet formation. This was a couple of years ago. Last week, we also published another system. This is in AstroPH now, where you have a very young star in the Fucus molecular cloud also that has an age of about 500,000 years and shows two concentric gaps that are consistent with the formation of giant planets at 50 and 85 AU. And this means that planet formation might actually happen much earlier than we thought before ALMA, and therefore the location of the world snowline at these very early stages could be important for planet formation. In ALMA cycle 2, a couple of years ago, we had a survey of these FURI objects that are undergoing these extreme events of accretion, and we found that these objects are dry, very large outflows and are also very massive. They have very massive disks. This is a low resolution image. Here is the disk, very, very small here, and you see the very huge outflow. But from this survey, we identify some targets that are very bright, which allow us to do a high resolution follow-up. In particular, we observed B883 Ori, which was the brightest and most massive of these FURI disks. We observed it with the longest ALMA baselines, and we obtained this image at 12 AU resolution, in which we see a very clear break in the intensity of the disk, about 40 AU. And this is consistent with a very hot, optically thick inner disk, and then a sudden break where the disk becomes optically thin. If we look at the temperature of this break, of this boundary here, it has the right temperature for the world snowline, which is around 140 Kelvin for the given density that you expect. And therefore, the interpretation is that inside, in the inner disk, you have dust and solid planetesimals that are very optically thick. And in the outer disk, the solids are dominated by snowballs and comets that have much lower opacities, and the disk becomes optically thin very quickly. This is artist's impression of the system. Again, you have the inner disk where the opacity is dominated by rocks and dust, and an outer disk where the opacity is dominated by water ice. And this is what you expect in every protoplanetary disk. This snowline should exist everywhere. But what is very interesting here is the location of the snowline, which we found at 40 AU, as opposed to what you would expect for a solar mass star, which is 3 to 5 AU. And B833 Ori is in fact a solar mass star. We have CO observations that we can see rotating around the star. So we have a Keplerian model which allows us to estimate a very precise dynamical mass, and the mass of the star is 0.3 solar masses. From the mass of the star and the accretion luminosity, in this case, the total volumetric luminosity of the system is 400 solar luminosities. And for this stellar mass and the age of the system, you would expect a photospheric luminosity of about 6 solar luminosities, which means that most of the luminosity is just accretion luminosity, and from this luminosity, you can calculate the accretion rate. And the accretion rate here is close to 10 to the minus 4 solar masses per year, and numerical models predict that for this extreme accretion rate, the world snow line is exactly where we see it at 40 AU. So what is happening here is that we have a solar mass in which normally the world snow line would be at 5 AU or 3 AU, but the star is undergoing these extreme events of accretion when the accretion increases 3 orders of magnitude for a short period of time, maybe 100 years. And these spikes are expected to happen several times during the formation of protoplanetary or planetary systems. And therefore, this is very likely to affect the formation of the planets. So what this means is that the world snow line cannot be considered static, right? It's not a boundary about 3 to 5 AU. This boundary will move in as the accretion rate of the star decreases, but on top of this, we can expect these accretion events that will move out very fast and the world snow line up to distances as far as 40 AU. And we don't know what this will do to planet formation, but very likely will destroy all the icy planetesimals, all the comets, and you will have to start the process of forming these comets again and again. So in conclusion, the planets that are currently in the habitable zones of stars in the main sequence, they probably form very dry, because they form inward of the world snow line, the protoplanetary disk. So this water has to be delivered to the surface of the planets by wet planetesimals that form outside of the world snow line. But this world snow line is very variable, especially at very young ages. And as we show, planet formation seems to be already happening even at 1 or even 500,000 years. So this means that planet formation models really need to investigate how these stellar outbursts will affect the formation of the planets and also the delivery of water to the inner planets that are in the habitable zones. That's everything I have. Thank you.